So today we're going to finish up the material for neurophysiology. What we're going to be talking about today is what happens at the synapse. So let's review just a little bit. We already know about resting potential. So resting potential, remember, can be anywhere. We can have resting potential here, we can have resting potential here, here, because it's all over the cell. And remember, resting potential is about minus 70 millivolts. And we know what creates resting potential. Remember, it's two things. One is the pump, that sodium-potassium pump. Remember, that pumps 3 sodiums out, brings 2 potassiums in, and it creates this voltage. But remember, we also have these leak channels. And so what happens is, as we pump in and out, we also leak in and out, and we set up this sort of steady state. And so we talked about that a whole lot. So that is resting potential. We also have talked a lot about graded potentials. And so remember, graded potentials, they vary in size. So you can have a little graded potential, you can have a bigger one, you can have a bigger one. Remember, the size is dependent on the stimulus strength. Graded potentials happen when you open a chemical gated channel or a mechanical gated channel. And the only place you have those is on the dendrites and the cell body. So the only place you can get graded potentials is over here, dendrites and cell body. Remember, a graded potential moves this thing towards 0. Well, there's also this point up here which is called threshold potential. And what happens at threshold potential, if you reach it, that graded potential turns into an action potential. So graded potentials generate action potentials. So the action potential doesn't happen until we reach threshold. So here's threshold potential. We have to reach threshold. Remember, they're all or none. You either get one or you don't get one, no matter how close you get. As long as you don't actually get to threshold, you're not going to get an action potential. But if you do, you're going to get an action potential. And so we spend a lot of time talking about action potentials. Remember, they happen when you open voltage-gated channels. And voltage-gated channels are only located on the axon, nowhere else. So the only place you can get an action potential is on the axon. You can't get one on dendrites, you can't get one on the cell body. And then remember, that action potential spreads down. It starts here, but one action potential creates another action potential, and then another one and another one. Remember, they're all independent events, just like dominoes falling. But the stimulus for the next one is the previous one, and it's going to travel down the entire membrane. And we talked about action potentials on a naked neuron, an unmyelinated neuron. And remember, if you don't have myelin, what you get is every little part of the membrane goes through an action potential. And so you have lots of action potentials. And remember, I use the analogy of trying to walk across the floor and touching every part of the floor. That is continuous conduction. And remember, it's slow. But we also have neurons that have myelin on them. They either are oligodendrocytes or Schwann cells. And what happens here is only the nodes go through action potentials. And if only the nodes go through action potentials, there's only going to be a lot fewer of them, and it's going to be a lot faster. And this is called saltatory conduction. So we have continuous conduction, and we have saltatory. And saltatory is much, much, much faster than the other one. So we know all that. What we don't know, or what we haven't talked about, is what happens over here. Because remember, this neuron right here, this one, can talk to this one. And so when they talk to each other, that's what we're going to be going over today. And it's what happens here at the synapse. So if you look at a synapse is basically just a junction. It's where one neuron connects to another neuron, or one neuron connects to something like a muscle or a gland or something like that. So if we were to draw it, here's our neuron, and here's our muscle cell over here. And so right there is the synapse where those two come together. And what we're going to get is a chemical or electrical transmission of energy. In other words, they're going to sort of talk to each other right here at the synapse. So let's look at synapses. So right here you can see a synapse, and this is also a synapse. Look, it's a junction between these two cells. It's where they come in close association. Well, there are different types of synapses, and we need to be able to talk about which neuron is doing the talking and which one of them is doing the listening. So when we look at a synapse, we have to figure out, is this guy doing the talking or is this guy doing the listening? Who's doing what? And we need some way to designate that. And so the one that's doing the talking is on the front side of the synapse. So it's called the presynaptic neuron. So this is the one that's sending the information. On the back side of the synapse is the postsynaptic neuron, and that's the one that's doing the listening. And so when we look at any one of these, we should be able to figure out who's doing the talking and who's doing the listening. Well, there are actually different types of synapses in our body. And the two types that we have electrical synapses and we have chemical synapses, and they don't look like each other. Look at this. Here's an electrical synapse. Look, those two cells touch each other. They actually touch. They're in contact. But here's a chemical synapse, and look, there's a space between them. They do not actually touch each other. There's a gap in between them. And so when we look at these, we're going to be able to tell the difference just by whether or not they're connected or whether or not there is this gap or space. That space is called a cleft. So if we blow this up and look at an electrical synapse, this is what it looks like. So electrical synapses are not very common in the body. We don't have very many of them. They're mostly in the embryo. That's where you find most of them. Now, we do have some in the adult in some brain regions, but they're very, very uncommon. But remember, these neurons are connected to each other. They're coupled. They're actually attached to each other. And so when you look at them, you can see this. So here's one neuron here, and here's another neuron here. And right there, they actually touch each other. And if you blow it up even more, it looks like this. So this is where they touch. And if you look where they touch, they have these channels. And these are actually just leak channels. And remember, leak channels are open all the time, and ions move through the leak channels. And it depends on where the concentration is higher, because remember, it always moves from high to low. So if our ion is sodium, and there's more sodium on this side in this neuron than there is in this one over here, what's going to happen is it's going to go this way. It's going to go through this channel and go this way. But if the sodium concentration is higher over here, again, it always goes high to low. If it's higher over here than it is on this side, then what's going to happen is the ions are going to flow this way. And so the information can flow in either direction. And so it's said to have bidirectional flow. It just depends on which side has the higher concentration, because remember, ions always move down their gradient. They always move down their gradient. And so we try to figure out who's doing the talking and who's doing the listening. Well, here it's a little more complicated. We have to see which way the ions are moving. So if the ions are moving this way, this guy's doing the talking, and this guy's doing the listening. But if the ions are moving this way, then this guy's doing the talking, and this guy's doing the listening. So this is a little bit like a conversation that you might have between two people. Think about a conversation. Usually with a conversation, one person talks, the other person listens, and then they switch off. The other person starts talking, and the other one listens. And so it goes back and forth, depending on who's doing the talking and who's doing the listening. So when we look at these electrical synapses, again, they're not very common, and they're coupled, they're electrically coupled, and they're bidirectional. Also, the communication is very, very quick. It's very rapid. It doesn't take any time at all, because all that has to happen is ions have to move from one side to the other. But that's not how most synapses are. Most synapses in the body are of this type. They're chemical synapses. Chemical synapses, when you look at them, they're completely different. First of all, the cells don't touch each other. There's a gap between the cells. Remember, that gap is called a cleft, a synaptic cleft. And then there's something else that's very different too. One side is always the one who does the talking, and the one who does the talking has these little packages inside this end bulb. Those are called vesicles, synaptic vesicles. And you don't have that on the other side. You don't have vesicles. What you have on the other side are channels with receptors. So there's a receptor over here and a channel over here. So look, the two sides don't look anything alike. And so the presynaptic neuron, that's this one, is always the one doing the talking. And the postsynaptic neuron, that's this one, is the one that always does the listening. So if you think about it, it's not like a conversation, it's more like a speech or something, because it always goes this way. The information only flows in this direction. And so if we look at that, we can see it. So here's our presynaptic over here. There's those vesicles right there. Here's our postsynaptic over here. And here's our channels with the receptors. And you can see the little receptors right here and right here. Basically, these are chemical gated channels, the things that we've already spent time talking about. They're chemical gated channels. So if we blow that up even more and look at it, it looks like this. So here's our presynaptic neuron over here, and here's our postsynaptic neuron over here. It's easy to tell them apart. This is the one with the vesicles, and inside are those chemicals, and those chemicals are called neurotransmitters. So we're going to have neurotransmitters, and they're going to transmit the message to the other side. And then on this side, we're going to have these channels, and the channels have these little receptors to receive the neurotransmitters. Don't forget, there's this space, which is called the cleft. And so these neurons don't touch each other. And so if you look at this, hopefully by now you can tell which one is the presynaptic, which one is the postsynaptic. Here's our pre, and here's our post. There's our little vesicles right there, and you can see these little green dots in here. Those are the neurotransmitters. And then over here, there's our little channels. And when you look at the channel, there's a little place right here for the neurotransmitter to bind. If we blow that up, it looks like Well, sort of. Looks like this. So look, there's the neurotransmitter right there. And then here, you bind the neurotransmitter, the channel opens and ions can flow. So let's go back and talk about how these synapses work. So if you look at it, it's a series of steps. It's a series of steps. And the first step is we got to have an action potential. So our action potential is going to travel down our axon all the way to the bottom of the axon. So if we look at this picture here, here comes the action potential. And it's going to travel down this axon all the way till we get to these end bulbs. Or in the area of the end bulb, right here in this area, there's a different kind of channel that we've talked about before. It's this one. It's a voltage-gated calcium channel. So think about this, voltage-gated calcium channel. Well, what's going to open it is voltage. That's what opens a voltage-gated channel. But it's a voltage-gated calcium channel. And so calcium is what's going to go through it. And remember, it always goes from high to low. Well, there's more calcium on the outside than there is on the inside. And so what's going to happen is when that action potential gets down here, we're going to open these voltage-gated calcium channels, and calcium is going to enter the cell. So that's our first step. Any questions about it? Well, we haven't done any communication yet. We just had our action potential and then calcium came in. But then what happens is that calcium that's on the inside, remember calcium came in, that calcium is going to be like a trigger for something to happen. And what's going to happen is all these little vesicles are going to start moving. They're all going to start moving down this way. And there's going to be more up here, and they're going to move this way too. And some of these are going to get all the way to the end, and they're going to fuse with the membrane. And when that happens, a little neurotransmitter that's on the inside is going to come out. In other words, we're going to get exocytosis of our neurotransmitter. And don't forget, it's caused by the calcium. The calcium that came in is what's going to cause this exocytosis of the neurotransmitter. And so now look, we have the neurotransmitter here in the cleft. The cleft has got fluid in it, and so this neurotransmitter begins to diffuse. Well, it diffuses in all directions. So it diffuses this way and this way and this way. It diffuses. And some of that neurotransmitter is going to wind up over here. Some of it's going to wind up over here. And it's going to bind to those channels. It's going to bind to the chemical gated channels. Well, if you look at these channels, they're chemical gated sodium channels. Look at sodium. So they're chemical gated sodium channels. And what's going to happen is when you do that, the channels are going to open and sodium is going to enter. So when the channels open, sodium comes in. And when that happens, remember when sodium has a positive charge, and what's going to happen to our potential over here is that it's going to move this way. So we're going to get a depolarization. So if we look at that another way, it looks like this. So here's those steps again. First we get an action potential, and then we get the calcium coming in, and then we get the vesicles moving and the neurotransmitter being released, and it binds to the channels, and you can see that right here. Look, it binds to the channel right there. And that channel is going to open, and sodium is going to enter. And so we're going to see sodium entering. And when that happens, we're going to get a depolarization. Well, as long as this channel is open, sodium can keep pouring in. So very quickly what happens is we're going to destroy the neurotransmitter. As soon as you destroy the neurotransmitter, the channel is going to close. So this happens very quickly. It opens, we destroy it, and it closes. And so if you look here, you can see the same thing. Here's our action potential, and it's coming down the axon. And when it comes down the axon, when it gets here, here are those voltage-gated calcium channels. Voltage-gated calcium channels. And so as soon as we get there, calcium's going to come in. And when the calcium comes in, it's going to cause these vesicles to move. And when the vesicles reach the bottom, they're going to fuse with the membrane and release the neurotransmitter. So we're going to get exocytosis of the neurotransmitter. And then as soon as they enter this cleft, they're going to diffuse. Well, again, they diffuse in all directions, but sometimes they're going to come into contact with that receptor and bind to the receptor. And when that happens, the channel's going to open and ions are going to flow. Well, depending on what ion it is, we're going to get either a movement this way, a depolarization, or a movement this way, a hyperpolarization. Does anybody remember what ion's associated with a depolarization? It's sodium. Anybody remember what's associated with a hyperpolarization? Which ion? It's potassium. So whichever channel we open, whichever ion moves, we're either going to get a depolarization or a hyperpolarization. And then remember, as long as that channel is open, we're going to continue to have ions flowing. So very quickly, we're either going to destroy the neurotransmitter, or we're going to actually reabsorb it so it can be used again. But as soon as it comes off of our receptor, as soon as that comes off, the channel's going to close. So, any questions about this? So you should be able to look at step 1, figure out what that is, look at step 2, figure out what that is, step 3, step 4. And then finally, we're going to get some sort of an effect, step 5. So here's step 1 again. Here comes our action potential. Step 2, we're going to open these voltage-gated channels, and voltage-gated calcium channels, and calcium is going to come in. Step 3, that calcium is going to cause these vesicles to move. And when they reach the end, we're going to release the neurotransmitter by exocytosis. And then step 4, it's going to bind to those channels. The channels are going to open and the ions are going to flow. And depending on what ion it is, over here we're either going to get a depolarization, or we could get a hyperpolarization. If it's sodium, we're going to get a depolarization. But if it's potassium, we're going to get a hyperpolarization. Well, in this picture, it's sodium. So sodium will enter. and we'll get a depolarization. But we could have the exact same thing over here with a different channel. And when the neurotransmitter binds, they open, and potassium leaves, and we would get a hyperpolarization. Any questions about that? You should be able to figure out what's happening at each of these steps, and you should be able to answer questions about it. So Zoe says hyperpolarization is a reabsorption. Now, hyperpolarization is, remember we have resting potential. And then we're going to have a stimulus. And it's either going to go this way, that's an excitatory stimulus. And an excitatory stimulus gives us a depolarization. Or this stimulus could make this go this way, and that's an inhibitory stimulus. An inhibitory stimulus gives us a hyperpolarization. And remember, we figured out the ions that are associated with it. This one is sodium, and this one is potassium. So if you look at this picture right here, it's sodium. So we're going to get a depolarization. But if this weren't sodium, if it were potassium, it would go this way, and we wouldn't get a depolarization. We would get a hyperpolarization. So instead of our graph going up, our graph would go down. It depends on which ion moves, whether we get a depolarization or a hyperpolarization. Any other questions? Okay, well, think about that. That was 5 steps. First, we had to have an action potential. And then we had to open channels and calcium came in. And then we had to have vesicles move. And then they had the release of the neurotransmitter. And then it had to diffuse across the channel. And then we had to open the voltage gate or chemical gated channels and so on. There are a bunch of steps. And so it takes time. So there's a delay here. And the delay can be as much as 5 milliseconds. It can be a long delay. So think about this. You can have a chain of neurons. Here's one neuron, and here's another neuron. But you could also have more neurons going to the same distance. So look, it took not 2 neurons to go to that distance. It took 4 to get there. So if they were both going to the same organ or something, which of these do you think would be faster, A or B? Which one would be faster? Remember, there's a delay, but the delay is here. So we're going to have one delay here, but we're going to have 1, 2, 3 delays here. So this one's going to be much, much faster, and this one's going to be much, much slower. So if you want to be able to tell an organ to move or do or whatever really, really quickly, we need to use fewer neurons so that we have fewer synapses. So one of the things that we want to happen really, really quickly is we want to be able to move our muscles really, really quickly. And so there's one neuron that goes all the way from the brain or the spinal cord all the way to the muscle. That way there's only one delay right here. That's it. We don't have any others. So this is going to be very, very fast. If we had the same situation to that muscle and it took this many neurons, then when we started to tell the muscle to contract, it would take a long time before it actually began to move. Because we'd have delay, delay, delay. That's why neurons are so long. That's why they're so long, because we don't have this delay, or at least very many of those. Does it make sense? Well, if we look at what happens here when we get this, remember, here is this sodium coming in. Well, if sodium comes in, it's going to go this way. But remember, I said it could also be potassium. It could be potassium leaving. So instead of sodium coming in, it's potassium going this way. And that would make this graph go down. And what we're going to have is a change in the potential on this membrane right here. Here's going to be a depolarization or a hyperpolarization. And so what we get are what are called postsynaptic potentials. So remember, postsynaptic is the neuron that's doing the listening. And what we're going to get is a change in the voltage over here. We're going to move away from resting potential. And we can either move this way or we can move this way. What we're going to get are graded potentials. Remember, graded potentials vary in size. Well, look at this. What if I have the situation here, and I've got 3 channels here. 1, 2, let's make it 4 or 5 channels. We got this many channels. And here's our vesicles here, and they have neurotransmitters in them. Well, what would happen if I released the neurotransmitter, but only this one channel opened? How big do you think my potential would be? Would it be big or small? The only place where ions are moving is right here. And I'm only going to get a little bitty change in voltage. But what if there's enough neurotransmitter to open 2 channels? So more ions are going to move. So this is going to be bigger. What if there's enough neurotransmitter to open 3 channels or 4 channels? It's going to get bigger and bigger and bigger. Remember, they vary in size, and the size is determined by the amount of neurotransmitter that's released. And then what we're going to get is we're going to get a change in potential. And remember, if it's sodium, it's going to go up. It's going to look like this. And remember, when it goes up, that's an excitatory stimulus. But if it's potassium, remember, it's going to go this way. And remember, if it goes this way, it's called an inhibitory stimulus. And so when we release the neurotransmitter and we get this change in potential, it's either going to be excitatory. If it's excitatory, we call it an excitatory postsynaptic potential. Excitatory because it went up, postsynaptic because that's where it's located, and it's a change in potential. But if it's potassium, remember, it's inhibitory, so it's going to be an inhibitory postsynaptic potential. Inhibitory because it goes down, postsynaptic because that's where it's located, and potential because that's the change in voltage. So we're going to get what are called EPSPs and IPSPs. So if we look at that, an EPSP is a depolarization. It goes this way. An IPSP is a hyperpolarization. It goes this way. And remember the ion that's associated with it when it goes this way? It's sodium. But the ion associated with it here is potassium. So let's look at EPSPs. So it's a sodium channel. So we're going to open the sodium channel. just like this, that sodium channel here. And sodium's going to come in faster than it usually does. And so our potential is going to move closer to 0. It's going to go this way. And remember, the size is dependent on the stimulus strength. So we can get small ones if you open a few channels, bigger ones if you open more, bigger ones if you open more, and so on. It's a graded potential. And so if we look at an IPSP, here's our channel. Here comes our neurotransmitter. It's going to bind right here in this receptor. And when it does, this channel is going to open and sodium is going to go in. When sodium goes in, the graph is going to move this way. So this is an IPSP. And if you graph it, it looks like this. There's an IPSP. So the stimulus right here is that neurotransmitter. So the neurotransmitter was released, the channel's open, sodium entered. And when sodium enters, this going to move in this direction. And then right here is where the stimulus ended. In other words, the neurotransmitter was destroyed and the channel closed. And then just like before, the way we get back to threshold is the sodium-potassium pump and the leak channels. Looks like this. If we look at an IPSP, it's going to be potassium, not sodium, potassium. And we're going to get a hyperpolarization. And so if we look at our graph, hyperpolarization is going to go down. And again, the more channels you open, the more it goes down. So potassium channel, potassium leaves, we're going to move further away from 0. We're going to go this way because 0 is up here. Again, the size depends on how many channels we open and how many ions flow. So look, here comes our neurotransmitter right here. It's going to bind to the receptor and the channel is going to open and potassium is going to leave. And when potassium leaves, the graph is going to go this way. So if we graph it, it looks like this. So here's our stimulus again. That's our neurotransmitter. Right here's when the channel's open. And when the channel's open, potassium is going to leave. And our graph is going to go down. But right here is where the stimulus ended, and we destroyed the neurotransmitter. And when you destroy the neurotransmitter, the channel closes. And just like before, the way we're going to get back to resting potential is the sodium-potassium pump and the leak channels. So it looks like this. We look at both of those together. This is what it looks like. There's sodium coming in. There's potassium going out. Any questions? So look, if we have an IPSP, here's 0. We start out at -70, so that's where we are. An IPSP is going to move the potential this way. But remember, we also have threshold. And this neuron has a threshold too. And the threshold, remember, is when voltage-gated channels open. So look, there's my stimulus. And then, but it only went that far. So it did not reach threshold. And if you don't reach threshold, you have a sub-threshold stimulus, then nothing is going to happen. We're not going to get an action potential. And that's the way it usually is, because one IPSP is just too small to reach threshold and give you an action potential. But look, if I stimulate it again over here, I'm going to get the exact same thing happening. It's not going to be any different. But look what would happen if I stimulate it twice, run right after the other. What's going to happen is this is going to go up, but before it has a chance to come down, it's going to go up again. And if I stimulate it again, it'll go up again, and I will reach threshold and get an action potential. So look, these three added together. And the word for adding together is summation. So summation happens when we add them together. So we can add IPSPs to each other. We can add IPSPs to each other. We can also add IPSPs with EPSPs, and they'll cancel each other out. So EPSP summation would look like this. So it would go up, up, up. IPSP summation would look like this. It would go down, down, down. They're adding together. So this is sort of like a positive number, and this is sort of like a negative number. But look what happens if you add a positive and a negative. They cancel each other out. This one's going this way, and this one's going this way. They cancel each other out. So that's when we have an EPSP and an IPSP at the same time. So look at this guy right here. So here's a neuron. There he is. And all these other neurons are talking to him. Look, this guy's talking, all talking. Trying to tell this neuron what to do. This guy's saying, make an action potential. This guy's saying, don't make an action potential. Make an action potential. Don't make an action potential. Make an action potential. Don't make an action potential. Don't make an action potential. So how the heck is this neuron going to know what it's supposed to do? Well, it's a little bit like being on a committee. If you've ever been on a committee, to make a decision, they sort of vote. And they count up the votes, and whoever has the most votes, if it's a yes, that's what they vote. If it's a no, that's what they vote. That's exactly the way things are happening here. So EPSPs are like yes votes, yes to an action potential. But IPSPs are like no votes, no to an action potential. And so what this cell does is it sits here and adds up all of the yeses and all of the nos. It adds up all the EPSPs and IPSPs. And if the final result is big enough to reach threshold, but you remember you got to reach threshold, then an action potential happens. Well, they're adding, summation. And there's actually two kinds of summation, two ways to add. One way is called temporal. Temporal means time. It's like tempo or tiempo, means time. And so with temporal summation, what we have is rapid fire order, one right after the other. So we're going to get a stimulus and a stimulus and a stimulus, one right after the other. It's usually one neuron, and it happens simultaneously. One right after the other, not simultaneously. And then the other one is called spatial summation. Spatial refers to space. And what we have here is several neurons firing at exactly the same time. So it comes from all directions, all happening simultaneously. So let's look and see what that looks like. Let's look at temporal first. So we have one neuron, a single neuron, rapid fire order, and then those IPSPs are going to add together. So look, here's our situation. There's our neuron, and these are the guys that are talking to him. A is talking, B is talking, and C is talking. So look, for here, this time only one neuron is doing the talking, and that's A. Nobody else is saying anything. So look, A says this. So it sends over a neurotransmitter. We open a channel. We get an IPSP right here. But look, that IPSP did not reach threshold. Here's threshold. So there's no action potential. Same thing next time. Look, we wait till it comes all the way back down to -70, and then we do it again. And look, it's exactly the same size, and so we're going to get exactly the same result. Did not reach threshold, no action potential. But look what happens if we do one right after the other. So it goes up, and it tries to come back down, but before it does, we send over another one and open more channels, and it goes up again. And as soon as we reach threshold, we're going to get an action potential. So temporal summation. So one neuron, neuron A, one neuron, and it's in rapid fire order. So remember, IPSPs are like saying yes. So this is saying yes, and this is saying yes, but this is saying yes, yes. So those two yeses added together. Rapid fire order. Let's look at spatial summation. So we're going to have more than one neuron, and they're going to fire at exactly the same time. So back here we are again. There's our neuron. But now look who's talking. It depends on which ones we're looking at. So here's A again. And this is what A produces, an IPSP. But look, it did not reach threshold. Just like before, it's too small. Same thing's true for B. When B talks by itself, look, there's an IPSP, but it does not reach threshold. But look what happens if A and B talk together at the same time. We're going to reach threshold, and we're going to get an action potential. So A added to B because they talked at the exact same time, simultaneously. And so their IPSPs add together, they summate. But let's go back now and look at this one, C. So look at C. C is an IPSP. So look, our graph is going to go down. We're going to get further away from threshold. So remember, this is like saying no. Well, if it says no by itself, this is what happens. But look what happens when this guy says yes and this guy says no at the exact same time. They cancel each other out. So we can have summation here where we say yes, yes, they're adding together. That's A and B. But we can also have summation where one says yes and the other one says no. That's AC. Both of these are summation. So if you look here, you should be able to figure out what's going on. So look, there's one neuron talking to another neuron, just one neuron. And look, they talk so far apart that these don't add together. So there's no summation happening here. So the guy says yes, and he waits a long time, and he says yes again. They're too far apart to add together. But here, same situation. There's E1 talking to this one, but look what happened here. So we said yes, and then we said yes almost immediately again. It's yes, yes. And they add together right here, and we get an action potential. That's temporal summation. That's temporal. One neuron sending IPSPs in rapid fire order, one right after the other. But look over here. Here we've got two neurons talking. Well, when they talk at exactly the same time, look, these two add together and we reach threshold. And so we get an action potential. And that's spatial summation because they're both saying yes at exactly the same time. And then if you look over to the last one, look, one of these is saying yes, but the other one is saying no. So here's our no all by itself. Look, it goes down. And then there's our yes by itself. It goes up. But when they're together, it cancels each other out. So this is temporal summation over here. But this is spatial summation here and here. So look at this and see if you can figure out. So without any of these words or anything like that, you should be able to look at this one and see these two don't add together. So that's no summation. It did not happen. If you look at this, remember there's one neuron and these two did add together. So this is temporal summation. And this is two neurons and they added together. So this is spatial summation. But remember, spatial summation can also add IPSPs with IPSPs if they happen at the same time. That's also spatial summation. Can everybody do that? Everybody understand? So, which one is this? Summation or no summation? What do you think? No summation. That's exactly right. There's no summation here. What about this one? When you look at it, what do you see? Summation or no summation? Summation, and the type is temporal. That's right. This is temporal summation. And then when you look at this one, what do you see? Summation or no summation? Yes, and then what type is it? Spatial, exactly right. And then finally the last one, summation. Yes, this is summation. We have two neurons, but remember one is an EPSP, one's an IPSP, so they're going to cancel each other out. It's still summation. It's like adding +2 and -2. You get 0, but you still added these things together, and that's what happens here. So this is still spatial summation. Everybody do that? Well, if you look at this, This is very, very, very simple. Look, the most neurons that we have here is just 3 neurons. 1, 2, 3 neurons. And that is just not the way the nervous system is. If you look in a person's brain or spinal cord, or brain and spinal cord, we have about 100 billion neurons. 100 billion. So here's 100 million. You got to add 3 more zeros. This is how many neurons the average person has. And they're all connected to each other. And one neuron is connected to about 10,000 other neurons. So it's not this simple. It's thousands of neurons connected to this one, and that one's connected to thousands of neurons, and each one of those is connected to thousands of neurons, and each one of those is connected to thousands of neurons, and each one. So there's a lot more going on than what we've just talked about. Sometimes neurons influence each other. They don't talk directly to each other, but they influence each other. So the simplest way I can talk about this is you use 3 neurons. Now remember, there's way more than that, but let's just use 3 neurons. So the effect of one neuron is going to be influenced by a third neuron. It's kind of like, you probably have seen this cartoon or something where you have this person and he's trying to make a decision, and like there's a little angel sitting over here on one shoulder. He's got wings. And here there's a little devil sitting over here on another shoulder, and he's got a pitchfork or whatever. And they're whispering in his ear. They're not making him do anything, but they're whispering in his ear, and they're influencing him. And that influence is going to change maybe what his decision is. That's exactly what we have here. It's influencing. So it's not a direct effect. And it can influence 2 different ways. We can have an influence that says, yes, do it. That's called facilitation. So it says, yes, go ahead and do that. But we can also have an influence where it says, no, don't do that. So think about your own self trying to make a decision in your head. And when you try to make a decision, you probably go through scenarios and you think about, is this going to be good or is this going to be bad? Am I going to get in trouble or am I going to do, is it going to help me? Is it going to hurt me? That's kind of what's going on in your head. And so there's more than these 2 neurons involved, like this guy. Remember we talked about him trying to make a decision? All of these people are talking to him. But look down here. This neuron cannot directly talk to that one. But it can talk to this one who is talking to this one. So this third neuron can influence the message that's coming across here. So this third neuron is sort of whispering to this neuron, say yes or say no. And once that happens, this neuron will either say yes or maybe it'll say no. But this guy has influenced the message. Well, in order to understand this, we have to go back to what we already learned, and that is here. Remember we said you have an action potential coming down here, and it opens these voltage-gated calcium channels, and the calcium is what causes the neurotransmitter to be released. Well, what do you think would happen if somehow these channels are blocked? They don't open. So when the action potential comes down here, There's no open. That means there's no calcium. Are these vesicles going to move? They're not. They're not going to move. And if they don't move, are we going to have the release of a neurotransmitter? There's not going to be any neurotransmitter. So what's going to be the effect over here? They're not going to have any effect. And that's how it works. It's going to work on this. It's going to work on these voltage-gated calcium channels. So let's look at it. So if you talk about facilitation, remember this is helping. It's saying, yes, do it. And so what happens here is we get more calcium channels. They become activated. So the very next time we get an action potential, more calcium enters. And when more calcium enters, more neurotransmitter is released. And when more neurotransmitter is released, we get a bigger IPSP, and so we're more likely to get an action potential. And so we have a facilitated getting an action potential. And so it looks like this. So look, here's our neurons. Here's the guy trying to make the decision. And this guy's talking to him. Well, our green neuron can't talk to him. It can only talk to this one. And so it can only influence what's going to be said. So if we blow that up and look at it, look, this is what happens. This third neuron releases a neurotransmitter that activates these channels. Look, there's the neurotransmitter. So now these channels are active. Now it doesn't open them. It makes them active. So the next time we get an action potential, now they're active, they can open, and so they do. And so more calcium comes in, and that's going to cause more neurotransmitter to be released, and that means we're going to get a bigger IPSP over here. So the green neuron helped the yellow neuron cause this purple one to get an action potential. So the green neuron facilitated getting an action potential. So you might think to yourself, when would this ever happen? Well, it happens constantly. Let's see if I can think of an example. Here's an example. What if you were playing softball? So if you think about softball, remember there's home plate, first plate, second base, whatever. Here they are, and you're out in the outfield out here. And basically you're so far out that nobody ever hits the ball to you, and so you kind of get bored. But then all of a sudden this big guy with big muscles comes up to the plate, and he's going to see, and you see that guy, and you know that he's going to hit it really hard, and it's probably going to come to you. Well, what's going to happen is we're going to influence how fast our muscles are going to work. This is the neuron that controls the muscle, but this third neuron is going to all of a sudden release this neurotransmitter, which is going to open these channels. And so the next time we get an action potential, our muscle works much faster. And so we can run around chasing the ball much quicker. In other words, your reflexes get faster. Because this sped up how fast this produced an action potential. So if you know about something ahead of time, in other words, you know this guy's a good hitter, and you know the ball might be coming to you, this third neuron can make this neuron more efficient at producing an action potential on your muscles. And so you can make the muscles react quicker. You increase the activity of your reflexes. So it happens all the time. So if we look at it, look at this. Here's our neuron here. Our neuron is X. Think about who can talk to X. Can D talk to X? Can D talk to X? Yes. Can C talk to X? Yes. But can E talk to X? No, E can only talk to C. So look, if I want to get an action potential on X, and C sends over an IPSP, this is what it looks like. And D sends over an action IPSP, this is what it looks like. Look, no action potential. But look what happens if before C sends over its neurotransmitter, E activates those channels. So the next time this action potential comes down here, I'm going to get more neurotransmitter. And more neurotransmitter is going to give me a bigger IPSP, and I get an action potential. So look what happened. E helped get an action potential from C. So E helped C. E facilitated C. Does it make sense? If E never says anything, this is how much neurotransmitter is released, and this is how big the IPSP is, and there's no action potential. But when E says something, this is how much neurotransmitter is released, and this is the size of the IPSP, and so you do get an action potential. Let's look at the other one. So this is inhibition. And so what happens here is we're going to inactivate calcium channels. So ahead of time, we're going to release a neurotransmitter that's going to make these inactive. And then the next time an action potential comes, they're not going to open. And so less calcium is going to come in, less neurotransmitter is going to be released, and I'm going to get a smaller IPSP. So I'm going to be even less likely to get an action potential. And so the effect is inhibited. So let's look at this one. So again, here comes the action potential. A certain amount of neurotransmitter is released. But before that happens, this third neuron releases this neurotransmitter. Look what happens. It blocks all these channels. They don't work anymore. They were working before, but they don't work anymore now. And so the next time the action potential comes down here, none of these open. Only this one opens. So that means less calcium is going to come in. That means less neurotransmitter is going to be released. And that means the IPSP over here is going to go from looking like this to look like this. And so I'm less likely to get an action potential. So if we go and look at this here, again, look who can talk to Y. G can talk to Y and F can talk to Y, but H cannot. H can only talk to F. So here's F by itself. Look what I've got. This big an IPSP. There's G by itself. I've got that big an IPSP. Remember, H can't talk to Y at all, so there's no IPSP. But I want to inhibit Y. And so this is how much neurotransmitter F was releasing. But now H is going to come here. We're going to block those channels. It's going to be less calcium, less neurotransmitter, and look what I'm going to get, an even smaller IPSP. And so I inhibited, I prevented it. So again, when would this ever happen? So here might be an example. Think about this. You go to the doctor, and the doctor decides you're sick enough that he's going to give you an injection. So he takes out a hypodermic syringe, puts a needle on it, and you're watching the whole thing, and then you see that he's going to poke this needle in your arm. Well, most of the time when someone pokes you with a real sharp pointed needle and it hurts, what you're going to do is you're either going to jerk away, or you're going to yell, or you're going to fight, or you're going to do something like that. But if you know ahead of time that you're going to get this injection, and it's a much better thing that you don't move, so what you're going to do is, this one cannot control the muscle. It just can't, because it's not connected to it. And so this is the neuron that controls the muscle. This is the neuron that would make you jerk away. So what this third neuron is going to do is it's going to release the neurotransmitter, block these channels, and even though this is going to hurt just as much as it would have otherwise, this neuron is going to prevent this neuron from telling the muscle to contract, because less calcium is going to come in. We're going to get less neurotransmitter, and so we're not going to get an action potential over here, and so the muscle is going to stay relaxed. It's not going to contract. So in this situation, if you know ahead of time that there's something going to be painful, or there's some reason that you need to not react, we're going to release this neurotransmitter, block these channels, and we're going to get a reduced reaction. And so think about some time in your life where you wanted to do something, but your brain is telling you, no, don't do that. It's holding you back. You might be in an argument and you want to punch somebody, but you don't. Your brain is holding you back. And so the muscles don't punch, they don't hurt or whatever, they don't move. So in other words, our reflexes can be enhanced. That's what this did. It enhanced our reflexes. So things got faster. Things got smoother. Faster, smoother, they work better. All because of this third neuron, because it helped. And then when we look at this other one, what happens is we're going to prevent the reflex. And so we're going to inhibit what's going on. And so we're not going to pull away. We're not going to jerk. We're not going to fight. We're not going to do those things, because this neuron says don't let that muscle contract. And so this one then doesn't produce as a big effect. And so the muscle stays relaxed. It's not just muscles, though. It could be lots of different things. But again, we've got facilitation. So here's facilitation. This one is helping. Helping get an action potential. And we've got inhibition. And this one is preventing or inhibiting an action potential. Does that make sense? Okay. Well, remember, we don't have 1 or 2 or 3 neurons. We have about 100 billion neurons. And they're not randomly arranged. They're all connected in lots of ways, but it's not random. And so there are these patterns of processing or patterns of connection. And one pattern is called serial. So serial is when the message travels along one pathway to a specific place. In other words, there's only one set of neurons to get to where we're going. Just one set. In other words, it's a little bit like dominoes again. So here's some dominoes. And the only way to make this domino fall is to do this. Push this one, and that one's going to fall, and that one's going to fall, and that one's going to fall. It's a series. That's why it's called serial. It's a series of events. So this one is going to produce an action potential, and then this one's going to produce an action potential, and then this one is, and we're going to get some sort of response, whatever it is. So a good example of this is reflexes. So here's a reflex. Look at it. There's a stimulus. It could be that hypodermic syringe we were talking about before. In other words, there's a needle. Well, the response to that, remember, is to jerk away. We remove ourselves from a painful stimulus. But look, it's a set of steps. It's in a series. First, there's a stimulus. That is going to activate a receptor. That is going to activate a neuron, a sensory neuron. That is going to go into the spinal cord and activate an integrative neuron. And that is going to activate a motor neuron. And finally, that is going to activate the muscle, and we're going to get a response. But look, there's only one pathway to this response, just one. It's like, again, a set of dominoes. Well, what do you think would happen if I were to go in and remove a domino? I'm going to take this one out. Well, look, what's going to happen is that's going to fall, that's going to fall, that's going to fall, that's going to fall, that's going to fall. But when I get here, this is what's going to happen. And there's not going to be any response. So serial processing is good in some ways. It's fast, but it's bad in other ways. It's all or none. You either get one or you don't get one. And it's fast, but if you damage any part of this series, it doesn't work anymore. And again, here are these 5 components: receptor, sensory neuron, integration, motor, and effector. Same thing here. Receptor, sensory neuron, integrative neuron, motor neuron, and effector. So look at this. Let's say you have to go to the dentist. So the dentist is going to decide that they need to drill on your tooth. You have a cavity or something. And they're going to drill down into your tooth. Well, that drill is going to hurt. And so the response here is going to be pain. And you're probably not going to sit still. You're going to jerk, you're going to cry, you're going to do all sorts of things because it really, really hurts. But look, you've got to go through all of these steps in order to get to the response, to it hurting, to jerking, and all of that. So there's only this one pathway to that response. Remember, it's like a set of dominoes. So your dentist, what they want to do is they want to remove a domino. They want to go in and take a domino out so that it looks like this. That's missing a domino. And so what they're going to do is go over here and somehow take one of these things out so you don't get the pain. It doesn't hurt. Well, it wouldn't do any good to block this because you'd still feel the pain. It wouldn't do any good to block this or this. And so what the dentist does is they use a numbing agent on this right here. It's usually something like Novocaine. You could also use benzocaine or lidocaine or something like that. But what happens is I'm going to drill here. There's going to be a big stimulus. That stimulus is going to activate this receptor like crazy, and I'm going to get action potentials, action potentials, action potentials, action potentials. But when I get to this spot right here, the action potentials don't go any further. So look, if the action potentials don't go any further, this is not activated. This is not activated. This is not activated. This is not activated. And there's no response. You don't feel any pain. So, look, it's a series. Well, that works great for things like reflexes. Works really good for reflexes. It's fast, it's all or none, all that stuff. But what it does not work well for is any kind of complex thought, any kind of complex thinking. Does not work very well at all. Because look, if this is the thought, whatever it is, the answer, and this is the only way to get to that answer, anything that interferes with one of these is going to stop this from happening. So brains don't use much serial processing. They use parallel processing. And parallel processing means that there's several pathways to the same response. And so if one pathway gets blocked out or doesn't work, it's broken somehow, there's still this pathway and this one to the response. And so parallel processing is very important for things like higher level thinking and for things like memories. And one stimulus can give numerous responses because there's several different pathways. So let's look at some of these pathways or pools. So one that's very common is called a diverging circuit. And so it's parallel processing, but look, it looks like this. What happens is this input begins to diverge into different pathways, and you can get different responses to that same stimulus. Now, if you do the PowerPoint here, what you're going to see is, if I asked you to think of an apple, so right here is apple. Well, if I asked you to think of an apple, you might think of a red apple that you kind of eat. And that apple might make you think of pie. And the pie might make you think of your mother because your mother makes good pie. And then when you start thinking about your mother, you think, oh, my mother, uh-oh, yesterday was my mother's birthday and I forgot it. And your response is, oh my God, I've forgotten my mother's birthday. And that came from the word apple. So that could be one response. But if I said the word to you, apple, you might not get that red apple in your head. You might think of apple like apple products. And so you think of Apple products, and then you think, oh wow, I'm thinking about my new Apple Watch. And then you start thinking about the watch, you might start thinking about that you can put music on it. And then when you think about music, you might start thinking about artists. And your favorite new artist is, I don't know who your favorite is, but I don't know, maybe it's Ariana Grande. And so look, when I said Apple, you wound up thinking about Ariana Grande, which is very, very different from, oh my God, I forgot my mother's birthday. So multiple responses from the same stimulus. Make sense? And so look, unless your mom is Ariana Grande, which I don't think she has any kids, those two things don't have a lot to do with each other. Here's another one. This is called converging. So what's going to happen here is it's going to get smaller and smaller and smaller until I usually wind up with one or just a few responses. It's the opposite of diverging. And so it might look like this. So look, there's multiple inputs here to a single response. And so instead of using the thing Apple, you might say, someone says to you, I saw a movie over the weekend. And so you think movie, okay. And then you ask your friend, what was the movie? And the person, your friend says, I don't remember the name, but it had, I don't know, Brad Pitt in it. So what you're going to do is you're going to start thinking of all the movies that you know that have Brad Pitt in it. And then you can come up with a bunch of them. And then you ask, well, what was Brad Pitt doing? And then you think that your friend says, well, he was a vampire. Well, there's probably only one movie where Brad Pitt's a vampire, and you come up with that movie. But it takes several inputs to get to the correct response. Another way that could have happened, though, is you said, I saw this movie and it had Brad Pitt in it. And you said, well, what was it about? And he was like, I'm not very clear, but it had Brad Pitt in it. And then you were like, well, what anything? I don't know, but it was Brad Pitt. And so you start thinking about every Brad Pitt movie that you've ever seen or heard of. And eventually, believe it or not, you might even come up with the right one. You might have to list 3 or 4 or 5, but still, you could come up with the right response. So these are both converging, but one has multiple inputs, and another one only has a single input. Here's another one. It's called reverberating circuits. Look, it's a circle. And circles don't end. And so there are certain things in our body we just don't want to stop. You don't want your heart to stop beating. You don't want to stop breathing. And so respiration is like this. It comes from the brain and the spinal cord, but it gets in a loop. And you loop and you breathe and you breathe and you breathe and you breathe. Another example of this might be something like when you get a song stuck in your head. Think about a song stuck in your head. Those are called earworms. So you get this earworm, and you just keep singing it in your head over and over and over, and you just can't get it out of your head because it's on this circuit. And in order for it to get out of your head, something big has to happen. So you might be in your car and it's singing and singing and singing in your head. But then you get in a car accident. And so instantly this gets broken because this is much more important. But guess what happens if you ever hear the same song again? It tends to get stuck in your head again. Singer-songwriters love these kinds of songs because once you hear it, it's something that happens over and over, and you get where you want to hear it even more. And then here's one more, and this one's actually my favorite. It's called a parallel after discharge circuit. So look, it's two pathways to the same output, but one pathway is fast. Look, that's a fast pathway. It's only got one synapse. But look, here's another pathway. This one is much slower. Look, there's a synapse there, there's a synapse, there's a synapse. This one's much slower. And so what happens is you experience the same thing multiple times. And so if you see, I don't know, a cat, a black cat, and so you see it with your eyes and it travels to your brain and it registers as a black cat. But that same input goes this way too. And so it's going to register as a black cat over here again. And so the second time you experience it, it feels familiar because you've already experienced it just a half a second or a millisecond before. This is what deja vu is. So deja vu is when you experience something and it feels like it's already happened to you, exactly the same way. And that's exactly this. This happened, and then that exact same thing, whatever it was, happened again just a millisecond later. And so you experience it twice, one right after the other. And the second time feels familiar because you've already experienced it once. You've already registered the black cat. Any questions? So that's the end of that chapter. That's the end of neurophysiology. And so there'll be a lecture quiz over this. It may not be out today, but there will be one.